10 on that same page, give or take. I prefer to work with these myself. I mean, so you can use equation 10 to solve variation of parameters problems in my course. That's fine. I am cool with that. In other words, what I'm trying to say is I'm giving you license to not rederive equation 10 for specific problems you're working. Every time we derive equation 10 from the differential equations, we're solving two equations and two unknowns, which isn't hard, but I feel like once I do it in general, then we should be allowed to use it, right? Now, that's not the answer either, is it, right? That's an ingredient in the answer. What's the actual... We're trying to solve the differential equation, right? So we can guess that yp is equal to v1 y1 plus v2 y2. What should we make y1 and y2 here? How about y1's cosine t and y2's sine t? Does that make sense? So here we get y1 cosine t and y2 is sine t, right? Right? Okay. So the Wronskian of y1 and y2 is the determinant of cosine t, sine t, right? So we get minus sine t here, we get cosine t there, we get cosine squared t plus sine squared t. The Wronskian is 1 if we use cosine for y1 and sine for y2. Be careful, if you reverse the role of sine and cosine, it makes the Wronskian minus 1. Which effectively flips the formulas in equation 10. All right, so now we can, borrowing from our general derivation, hence v1 is what? It's going to be the integral as, what's a equal to? I've erased it, but we were bouncing off the general template. I mean, the general form ay prime prime plus by prime plus cy equals to f, right? So by comparison, a is what? It's 1, right? A equals 1. So in the formula 10 over there, there's the a is gone. In fact, it's kind of, let's see here. A is equal to 1. F is equal to secant of t, right? So we're supposed to do like what? Minus f times y2 divided by a times the Wronskian dt. Putting in the details here, what is that? That's minus the secant of t. What's y2? y2 was sine of t, right? And divided by 1 times 1. I'm writing it out just so you understand the moving parts here. Although many of them are kind of, they go away, right? 1 times 1 is 1, and division by 1, well, you know. So what do we have to integrate? We have to integrate. Yeah, tangent. So sine t dt over, looks like cosine t, right? There's a minus out here, yeah? And so that's really just the integral of d cosine t over cosine t, yeah? Some of you have had Dr. Wang. You're familiar with this notation? Let u equals cosine if you don't know what I'm doing. Anyway, the point is that this is the natural log of the absolute value of cosine t plus some constant, right? Let me call it constant c1, and I'll show you why I do that in just a second. So there's my v1. How about v2? What's v2 going to be equal to? So that's f y1 over a times Wronskian dt. Equation 10, right? And that is actually the integral of what? It's the integral of, this one's kind of funny, isn't it? So you got secant t cosine t dt. But secant's what? It's 1 over cosine, right? So this is funny, just the integral of dt. And so we get t plus c2, let's say. Now, I say plus c1 and plus c2. You really, it kind of depends on how you want to do things. If you add constants here and here, it turns out that this isn't really yp, it's the general solution, right? So let me just write that down. So yp equal to, what was it? v1, natural log the absolute value of cosine t plus c1 times cosine t plus t times plus c2 sine t. All right, let me write that. So really the general solution is cosine t times the natural log of the absolute value of cosine t plus c1 cosine t plus c2. Sorry. Plus t sine t. I'll get it eventually. Plus c1 cosine t plus c2 sine t. What I'm trying to tell you guys is you have choices. If you add constants in v1 and v2, those will become the constants in the general solution, right? So if you want to, you don't have to add constants in the integration in equation 10. If you don't, it's fine. The constants just come from the general theorem I wrote at the start of today. The general solution does need two constants, c1 and c2, for a second order problem, right? There's got to be there to adjust for possible initial conditions. I have not done an initial condition problem today yet, have I? You can take everything we did today and add initial data to it and find the c1 and c2 for it. Why didn't I do that? Really no reason. It's something we can always add on to any problem. I just don't, I mean, there's enough burden intellectually with what we're doing without adding that in the midst. So that's why I didn't do it. Any questions about this? So here's the story. If you have a non-homogeneous problem and undetermined coefficients doesn't work, you use variation of parameters. To use variation of parameters, you have to find the fundamental solution set, and then you use equation 10 to construct the solution. Equation 10 is not the solution. It is an ingredient to make the solution like this. Okay? Just like with exact equations, if you box the f, that's wrong. F equals to blah is not the answer. The equation that gives you f equal to a constant, the solution set to that is the solution to an exact equation, right? In the same sense, v1 and v2 are not the answer here. They're an ingredient for making the answer, right? So you guys are like, well, I think I'm just going to end 10 minutes early, if that's all right with you guys, rather than, I mean, we're not there yet. Oh, we're getting there. Let me try to wrap things up here. Just show you a few things from the notes. You'll forgive me if I don't get everything. Don't worry, we're not doing series solution techniques. Well, not today. That would be mean. All right, so I've probably shortchanged the applications a little bit. So I tell you what, I won't put a spring problem on the test one. Sound like a good deal? It's probably a good deal. So variation of parameters is also true in the nth order case. In the nth order case, you have a fundamental solution set with n things. So this is the particular solution. You differentiate it. And again, we're going to assume that the terms with derivatives on the v, the terms of that, like these ones, the y1, I'm trying to remember which one it is. Oh yeah, we set this equal to 0. again. And then we keep differentiating. And so constraint 1 is just like our constraint. Differentiate again. After you differentiate again, we get that. And the second constraint would be rather v1 prime, y1 prime, equals 0. So you keep doing this, you keep getting more and more constraints. And then again, you can rewrite them as a, this is kind of awful. But after the dust settles, you get this system of n by n equations with the fundamental solutions, their derivatives, their second derivatives, all the way up to their n minus 1th derivatives. That matrix times the derivative of the undetermined functions is equal to that vector where the inhomogeneous term appears in the last slot, divided by the leading coefficient of the differential equation. Again, that's the Wronskian. Well, the determinant of that's the Wronskian, so we know it exists and it exists and it's non-zero. I mean, that matrix is invertible, more to the point. And so you can solve and integrate, and there is, in fact, an nth order variation of parameters. It's quite awful. Now, you guys know Kramer's rule, some of you, maybe. And so you can use Kramer's rule to solve these equations too. I could have used Kramer's rule to solve these. If I had used Kramer's 2x2 Kramer's rule on our n equals 2 case, it would have produced equation 10 just the same, right? And, oh, yeah, I sometimes forget this system also works for n equals 1. N equals 2 is where I usually think of variation of parameters. And, oh, here's the example we just did, except with x instead of t. Here's another second order example. This second example is actually important. I might ask you to solve a problem. I might say, find an integral solution for the problem, right? That means that the solution's in terms of an integral. This is such a thing. Variation of parameters actually allows you to do that in a pretty nice way, right? You can find an answer in terms of an integral. And here's a token third order example, but I will not test you on it. I want you to know that there is variation of parameters for higher order systems, but I also want you to know that because I like you guys, I wouldn't test on it. Or even ask you to do a homework problem on it, honestly, because they're unpleasant. Now in the regular semester, I might ask them to do some homework problems. You're like, haha, summer for the win. It's here. Reduction of order is a general technique. Here's a page or two of notes on it. Operator factorizations, just something that I'd like to spend more time on, but we don't have time. So, oh well. Cauchy-Euler problems we'll get back to eventually. Applications, I talked to you a little about springs without damping. I should mention the terminology. So the springs, since you either have distinct real roots, you have a repeated root, or you have a complex root. Those are the three cases for the spring problem, because it's a quadratic equation. You either have distinct real roots, a repeated real root, right, or a complex root. The case of distinct real roots, I believe, is called overdamped. For example, this problem, if I have a damping constant of 3 and a spring constant of 2, I get characteristic solutions -1 and -2. This is an example of what's called overdamping. Critical damping is when you have the repeated root, so this would be the solution, something like that, right? Then underdamping, I think also sometimes called weakly damped, is the case when you have a complex root. In that case, you have something like this, right, is your solution. And so graphically, it's like you've got this envelope, this exponential envelope, right? And then your solution is doing something like this between that. Now, so it's decaying to 0, right? But it's kind of like that. So if you think about, I mean, where's the physical example of something that springs with friction? Well, your car has shock absorbers, right? What are those? It's a spring and a can of oil, right? And you can adjust the viscosity of that oil in your manufacture of this to achieve a certain damping coefficient, right? And so, like, what you don't want to happen is this, right? If your springs on your car produce this kind of oscillation, that's annoying. But you've seen this happen to people, right? They hit a bump on the highway and they just kind of keep, right? You'd much prefer the case of critical or overdamping, right? Because that has a motion that looks more like this. maybe it dips below and comes back. I don't know, but it's pretty. It zeroes out faster. So you want to avoid, in like shock absorbers, you don't really want underdamping. There's, for you electrical engineers, the RLC circuit's the same math. The correspondence is that math is like induction, inductance, the beta, the damping coefficients like resistance, the spring constants like 1 over the capacitance. And so I have some problems like that here. And finally, just to mention, I won't work out the derivation today because we're out of time, but here I mentioned earlier that the problem of resonance is really to pick a gamma that gives you the maximum amplitude of the response function. So you can actually work this out symbolically, and if you do that, the homogeneous solution looks like this, so it's definitely not the same form. There's no overlap. The particular solution has to have the form A cosine plus B sine gamma t like that. Plug it in. You work out the math. Eventually, you get to your particular solution looking like this. So if you want to choose gamma, and by the way, the amplitude of this is that. So if you want to have the maximum response, you want to differentiate this with respect to gamma, set it equal to 0. And when you do that, that gives you the criteria for resonance, which is right there. So the resonant frequency, if it exists, is the square root of k over m minus beta squared over 2m squared. It takes me about a half hour to work this out. I'm sorry I didn't find time for it this summer. My apologies. If you go back in previous years, you'll find me work it out. And then I do the same thing for RLC circuits, except I use complex notation to derive the same thing. So if you want to provoke the maximum voltage response in an RLC circuit, you want to apply this kind of frequency, 1 over LC minus r squared over 2l squared. But that's resonance. That may or may not exist. There's some where the maximum response is like DC. So DC would be 0 frequency. I've inadvertently, well, anyway, it's a long story. Let me shut up, and I'll see you guys Monday, I guess. So anybody, if you just come with me after class, if you don't want me to, I'll probably just tape your solved quiz to the door once I'm done here today, and so you can come and get it over the weekend or today, whatever you want, all right?